This video is about specific heat capacity and the formula that we use to calculate the amount of heat transferred. And we'll start by looking at three comparisons. And the first one is if we want to heat up 1 kilogram of water from 10 degrees Celsius to 20 degrees Celsius. And we also want to heat up 2 kilograms of water from 10 to 20 degrees. How do these two differ? How much more heat do you think we're going to need for the 2 kilograms of water? Well, it's quite simple because we've got twice as much mass. So heating up 2 kilograms of water is the same as just heating up 1 kilogram twice, isn't it? So that means that there's going to be twice as much heat transferred when we're heating up 2 kilograms of water. Right, so the next example is if we're heating up 1 kilogram of water from 10 to 20 degrees Celsius again, but we also want to heat up 1 kilogram of water from 10 to 40 degrees Celsius. How do these two compare? Well, the temperature difference in the first one is 10 kelvins, or 10 degrees Celsius, it's the same thing. And in the second one, we've got 40 minus 10, which is 30 kelvins. So the temperature difference in the second case is actually 3 times as big as the temperature difference in the first. So that means that we're heating it up by 10 degrees, and then we're heating it up by 10 degrees again, and then 10 degrees again. So we actually have to do 3 times what we did in the left-hand side example, which means that the amount of heat needed from 10 to 40 degrees is 3 times as much. And the final example is if we want to heat up 1 kilogram of water from 10 to 20 degrees Celsius, but also 1 kilogram of copper from 10 to 20 degrees Celsius. Now, this is not as obvious because we need to know a bit about water and copper. So you might have noticed that metals are easier to heat up and to cool down, whereas water is a bit more difficult to heat up and to cool down. So water contains more energy when it's hot than copper does. And you're not expected to know what the difference is, but it turns out that 1 kilogram of water uses up 11 times as much heat to heat it up from 10 to 20 degrees than 1 kilogram of copper. And that's because of their difference in specific heat capacity. So these three examples, they show 3 different things in turn. So the first one showed us that the heat transferred was proportional to the amount of mass that we were heating up. The second one showed us that the heat transferred was proportional to the change in temperature. And the third one showed that the heat transferred was proportional to specific heat capacity, which is the property of the material, and we call it C. Now, combining all these 3, we can come up with a formula for calculating the amount of heat transferred. So we get Q equals mc delta T, because the heat was proportional to all these 3 things. And in this formula, Q stands for heat, and it's measured in joules. M stands for mass in kilograms. Delta T is the temperature change, and it's measured in kelvins. And C is the specific heat capacity. And units of that you can work out by rearranging it, because we know that the units have to be the same on both sides. So the unit turns out to be joules per kilogram per Kelvin, because that way we have joules on the left-hand side of the equation, and then we have kilograms times kelvins times joules per kilogram per Kelvin, so we end up with joules on both sides of the equation. Now let's write down the formal definition of specific heat capacity. So the specific heat capacity of a substance is the amount of energy transferred to or from 1 kilogram of that substance for each 1 Kelvin change in temperature. And each substance has its own specific heat capacity. So, for example, water has 4,200 joules per kilogram per Kelvin. For air, it's only 1,000 joules per kilogram per Kelvin. And for copper, it's only 390 joules per kilogram per Kelvin. So what does this actually mean? What difference does it make? Well, let's look at 100 grams of water and 100 grams of copper. And for each of them, we're gonna start with the material at 20 degrees Celsius, and then we're gonna heat it up to 100 degrees and then cool it back down to 20 degrees. So first of all, for water, when we want to change the temperature from 20 to 100 degrees, that's a temperature difference of 80 degrees, isn't it? So if we plug all this into our formula, we got Q equals mc delta T, and the mass is 100 grams is the same as 0.1 kilograms, and the specific heat capacity we wrote just above, and it's 4,200. And finally the change in temperature we said was 80 degrees. So if we multiply all these three together, we get 34 kilojoules. So we had 34,000, and then that was in joules, and then we changed it into kilojoules to make it look a bit nicer. So that's how much energy we have to add to the water to heat it from 20 to 100 degrees. And because everything here is reversible, that means that cooling it down from 100 degrees to 20 degrees is actually going to release the same amount of energy that we added before. So we don't have to do any calculation again for this. We can just write down that the amount of energy we have to take out of the water to cool it down is also 34 kilojoules. Now let's do the same thing for copper. So we have copper at 20 degrees, and then we're going to add energy to it to heat it up to 100 degrees Celsius. And we use the same formula. I'll let you do the calculation yourself to plug in all those numbers into the formula, and you should get that it's 3.1 kilojoules added. And that agrees with what we had on the previous page, which was that the water took 11 times as much energy to heat up as the copper. And 11 times 3.1 sounds like that should be about 34, so that sounds alright. And then from 100 degrees we're going to cool down the copper back down to 20 degrees Celsius, and we do that by removing the same amount of energy. So we're removing 3.1 kilojoules to get back. So you can see that the material that had a lower specific heat capacity, which was copper, ended up being easy to heat up, but also easy to cool down. And when I say easy, I just mean that less energy is involved. Now, I don't blame you if you're wondering why different materials have different values of specific heat capacity. Is it just there to be annoying? Well, I'll try to explain why by looking at what the heat that we add to a substance does to a substance. Where does it go? So there are three different types of energy that the heat goes into. One is the translational kinetic energy of the molecules. Another one is increase in the potential energy of the molecules. And the third one is to increase other kinetic energies, so rotations of molecules or vibrations of atoms within the molecules. So these are all three types of energy that we talked about in the internal energy topic. And all of the three energies together combine to give an increase of internal energy. So internal energy is all of these, because as you remember, it's the kinetic energy plus the potential energy. But only the translational kinetic energy of the molecules is what we measure when we measure the temperature. So only one of these three things leads to an increase in temperature. So we're adding heat, and that heat is going into three different types of energy, but only one of them is what we measure as temperature. So the reason why materials have different specific heat capacities is simply that these three things happen in different proportions in different substances. So it depends on the structure on the molecular level. So it's going to be different if we have a molecule made of 2 or 3 atoms. That's different from if we just have monatomic particles. Because monatomic particles, we don't really have to worry about rotation or vibration. So because of the different proportions that these things are going to happen, that's why we get different specific heat capacities for different materials.